Great. Well, welcome, everybody. My name is David Sandalo. I'm the inaugural fellow at the Center on Global Energy Policy at Columbia University, and I'm thrilled to welcome you to a discussion of how artificial intelligence can help reduce emissions of greenhouse gases. Along with several colleagues and friends, we're going to present some work that we've done on that topic, specifically a roadmap that we released in November of this year. The plan is we're going to present the highlights of that roadmap for about a half an hour, and then have a conversation, take your questions. So please, if you've got questions, put them into the chat, and we look forward to engaging with all of you on your questions on this topic. We're also delighted to get into this week's breaking news involving DeepSeek and related topics and energy use for AI more broadly. It's all very relevant to the topic we're going to be discussing today. Let me start by introducing my colleagues here and co-authors of this book-length report that we did, starting with Julio Friedman, who's the Chief Innovation Officer at Carbon Direct, a former scholar at the Center on Global Energy Policy. You can never really go away, Julio. Great to see you. Colin McCormick is the Chief Innovation Officer at Carbon Direct. He teaches AI policy at Georgetown. And a longtime colleague, and Alp Küçükkelbir is the chief scientist at Faro Labs, teaches AI both in the computer science department and the School of International Public Affairs at Columbia University. At the last minute, unfortunately, our colleague Mikal Nakmani is unable to join us. We were hoping she was going to be able to be with us. She played a very central role in the preparation of this roadmap. But was pulled away at the last minute, is unable to join us. So with that, let me share my screen. And can everybody see that? Tremendous. Well, you have here three of us, or four total, three plus me, to discuss this roadmap. But I want to highlight that this roadmap had 25 co-authors total. It was really a great team, and we're really honored by the opportunity to work with so many of our colleagues here, and it's a great and very large team effort. The topic that we looked at in this roadmap is pretty straightforward, and it's really the title of this session, which is how can AI help reduce emissions of greenhouse gases? Pretty straightforward. There are overall 17 chapters. And each chapter has 5 to 10 recommendations. We decided at the beginning of this project that we wanted to do more than just talk about this issue. We wanted to provide specific actionable ideas to stakeholders of all different kinds about what they could do to help artificial intelligence reduce emissions of greenhouse gases. And so every chapter has 5 to 10 recommendations. The roadmap is available online here at these 3 different URLs, including at Academic Commons, columbia.edu. We'll send around this slide deck to all of you who have signed on, so you can scribble down the URLs if you want, but we'll send this around. And a hard copy is going to be available on Amazon soon. We're hoping it's going to be available as soon as next week. Here's our table of contents. We have, as you can see, 3 sections: a background section, and we hope this volume is a useful resource for people who may not have background in either AI or in climate change. And so we have chapters introducing each of those topics. We then have a section that looks at 8 different sectors and how AI can be used to reduce emissions in those sectors, and then a number of cross-cutting topics. There's a lot of detail in our book's 334 pages. So let's start just by boiling down 5 key takeaways, just the top level messages here from our book. The first is that AI has the potential to make significant contributions to climate change mitigation in the years ahead. And that's, I think, worth repeating. AI can make a big difference here in fighting climate change. It can contribute incremental gains, and we'll talk about ways it's already doing that. Just one example out of hundreds is it's already increasing output at solar farms. And we believe there's opportunities for transformational gains as well. And we'll talk about some of those. One of them is helping discover important new materials for clean energy technology. So, maybe our first and most important conclusion is that AI has the potential to make significant contributions to fighting climate change. We also looked at how much greenhouse gas emissions are coming today from computing operations from AI. The literature on this is not as good as it could be, but based upon the existing literature, we think that at this moment, emissions from AI are less than 1% and probably much less than 1% of total greenhouse gas emissions. But those emissions are very likely to rise in the near future as power demand for AI increases. And then in the long term, there's the potential for AI to increase or decrease greenhouse gas emissions. Either one of those futures are possible. And we hope that one result of this work will be to contribute to AI's decreasing greenhouse gas emissions, contributing to solutions to this problem, not making the problem worse. We look in almost every chapter at the barriers to AI making a difference. The main barriers to AI making a difference here are the principal ones we conclude are a lack of data and a lack of trained personnel. A fourth key takeaway is that trust in AI systems is essential. In order for people to adopt AI and use it for good purposes, it needs to be trusted and trustworthy. There are a number of barriers to that, and we talk about those. And then a fifth observation, a fifth takeaway is that every organization with a role in climate change mitigation should consider opportunities for AI to contribute to its work. If you're working on this issue of fighting climate change, we recommend everybody at least explore how AI can help you in doing that. So with that, let me turn the floor over to Dr. Alp Kuchu-Kelber, who wrote our chapter on Introduction to AI.
Thanks so much, David. So artificial intelligence has a variety of definitions. We adopt the following one for the purposes of this report, which is the science of making computers perform complex tasks that we traditionally associate with human intelligence. So on the right-hand side, we have an example here of a software program playing Go against the world champion. Next bullet point, please, David. Now, AI is a form of software, but it differs from traditional software in that instead of relying on explicit programming, it relies on historical data and simulation to, quote, train models and, quote, learn patterns, both words that we associate with human intelligence. So the picture on the right shows an example of how data becomes an important component of building artificial intelligence systems, and we will discuss both the availability, accessibility, and other properties of data throughout all of the examples we bring up in this report. Now, modern AI has four far-reaching capabilities that are already pervasive in our lives. AI can detect patterns from data used in technologies such as facial recognition. It can make predictions, such as predicting the next word in a sequence of words, like in large language models. It can optimize, such as optimizing the best route for you to take from point A to point B. And it can also simulate, such as various video games do. Now, each of these have examples in terms of applications to climate change. A few of them are presented here on the slide, and we will go into deeper examples of these throughout the next few slides. Next slide, please, David. Back to you.
Excellent. If you're here likely to because you're concerned about climate change. This concern is warranted. Atmospheric concentrations of greenhouse gases, notably CO2, but also others, are higher than at any time in human history, and really any time in many millions of years. For CO2, probably over 40 million years. And this is manifesting in consequences we see around the world. The warmest day ever recorded in human history was last year in July. 2023 was the warmest year in history by a lot. 2024 was the second warmest year, also exceeding all previous comers substantially. The 10 warmest years on record were the last 10 years, et cetera, et cetera. The consequences of this are far-reaching. Drought, which leads to increased risk of wildfires. This is one of the contributors to the Los Angeles fires recently. Heat waves is a big one. Impacting human health and loss of life. Everything from beetle kills and crop failures to raising sea levels. All of these things are consequences that were predictable and predicted more than 20 years ago in climate change, and we're seeing the manifestations of them now. One of the surprises is, in fact, that many of these consequences are manifesting earlier and more acutely than originally predicted. Next slide.
And we just want to jump in and say that we are very grateful that the lead author for this chapter in our report was Dr. Hosang Lee, who was the just left as the head of the Intergovernmental Panel on Climate Change, and we're really grateful for Dr. Lee's contributions to this report.
Indeed. In that context, go back one quickly. We looked at 8 different sectors across the economy and looked in each case about how AI might be able to reduce emissions, remove emissions as part of that. This is far ranging. We cannot cover all those topics today just in the interest of time, so we've selected a few to talk about. In that context, I hand it over to Colin to talk about the power sector.
All right, thanks so much, Julio. So let's start by noting that everyone on this webinar is probably familiar with the fact that the power sector is a major contributor to global greenhouse gas emissions, maybe 28%-ish. And decarbonizing it is absolutely crucial for achieving climate goals and deep economy-wide decarbonization. Next point, AI already is helping in some ways to decarbonize the power sector. A couple of immediate examples on that are during the siting process, deciding where to put solar and wind power, also where to put transmission lines. AI can help optimize those decisions before construction. And then in an operational context, AI can also maximize the clean electricity output of solar and wind farms. Next bullet. But there's a lot more. There's many other ways in which AI can contribute. One emerging area is around maximizing power flow through existing transmission lines, a technique known as dynamic line rating, which allows utilities to put more power through a particular transmission line at certain times of day and year, depending on temperature conditions. AI can also support analysis of power flow through a network. That can be part of a planning process and can also be operationally active. One more to comment on here is many people may have heard of the interconnection queue backlog, particularly in the US. Thousands of gigawatts of solar, wind, and batteries are taking years to move through a regulatory review process. AI, perhaps large language models, can help speed that up. Plenty of barriers, unfortunately. They include a lack of standardized data, a lack of trained personnel, and certainly in some cases, a utility business model and perhaps a culture that is not particularly comfortable with adopting advanced software AI technologies. It's also really important to note that in any real-time operations, such as the operation of the power grid, using AI can introduce security and safety risks, so that operational context must be thought about extremely carefully before it's implemented. Let's go to the next slide. Another sector we highlighted is aviation. When people think about greenhouse gas emissions from aviation, obviously the main thing that comes to mind is CO2 emitted in burning jet fuel. That CO2 is emitted to the atmosphere and is a key to the greenhouse gas impacts of aviation. Emerging science is helping us understand there's another important contribution, which is the formation of persistent contrails. These are the white streaks behind some airplanes that you've probably seen in the sky. A small number, maybe 5 or 10% of those, persist for long enough to affect the radiative balance of the Earth. They trap outgoing infrared that would otherwise have left the surface of the Earth and cooled the planet. That's a net warming effect. It's roughly of the same size as radiative forcing from CO2. AI can help predict when and where aircraft will form those contrails and recommend relatively minor altitude changes to prevent that from happening. Looking at sustainable aviation fuel, it's important to test properties of new fuel formulations. But before going to testing, it's possible to use AI to simulate, for much cheaper, simulate and predict what those properties are likely to be. Aircraft design, improving efficiency of wings, aircraft bodies, etc. Conventionally is done with computational fluid dynamics calculations. Those are expensive and slow. AI can speed that up and allow faster iteration times. Virtual wind tunnel testing is one form of that. And finally, for airport operations, optimizing the use of runways and minimizing unnecessary idling and circling by aircraft minimizes unnecessary fuel burn and emissions. Plenty of barriers in this sector as well. Most regulations around aviation are principally focused on safety and may not have appropriate accommodations for the use of AI. And of course, skilled personnel are necessary in this sector as well. Great, I'll hand it over to Alp for the next sector.
And happy to get all the items on the slide, David, here to minimize the back and forth. Perfect. So manufacturing is another difficult to decarbonize sector. It makes up a huge portion of the carbon footprint. And AI has both incremental and transformational opportunities to change how we manufacture products. One example that we'll highlight here is around that direct process of making things. On the right side, you have an example indicating how manufacturing of commodity products such as steel, cement, and chemicals is increasingly moving towards using recycled feedstock rather than relying on virgin feedstock. The idea here is to create a circular material economy rather than a linear one. And so recycled feedstock introduces new sources of volatility, and AI offers the opportunity for these manufacturers to adapt these sources of volatility both faster and better. Including the shortage of AI expertise for the deployment of AI, there is an also increasing worry around expertise retention within manufacturing. So AI offers the opportunity to leverage historical data to ensure that best practices of how to operate facilities are maintained and available to even young employees who are getting started. Other applications of AI within manufacturing include opportunities to improve the yield of certain chemical reactions, to minimize the amount of energy consumed, either in terms of direct electricity or heat, as well as the ability to switch to different energy options, among other applications. Back to, I think, Julio.
Thank you, Alp. Existing capital stocks exist. There are steel mills, there are power plants around the world that are going to run for a very long time. And in fact, whoops, what happened there? Can we get the slide deck back up? In addition to that, we are seeing a ramping up of emissions due to the increased use of combined cycle natural gas plants, due to new manufacturing centers around the world. Manage those carbon dioxide emissions, carbon capture ends up being a very useful and important tool. According to the Intergovernmental Panel on Climate Change, between 12 and 20% of abatement will be done with carbon capture. AI can help. A critical pathway is just discovering new carbon capture materials that can dramatically reduce the energy required to run these things. In addition, AI can help us design new reactors of various kinds. We have a set of designs that are just fine, but I'm sure that we can have better heat integration, better capital efficiency, more energy efficiency, all these other sorts of things. That's all on the capture side of the business. In addition to that, you have to transport and store the CO2. AI has already begun to be used to optimize the transportation networks, pipelines, barges, rails, etc. Please go back. We are, in fact, already not just optimizing for cost or for volume, but also for things like minimizing environmental impacts, serving disadvantaged communities. The same thing is true for storage. AI can better understand in new areas whether or not the geology is well suited for that, and what is needed to proceed. AI can play a very large role in accelerating the permitting of these things. Right now, the wait times are quite long, and we can do better and help communities understand the potential trade-offs and risks and lead to better community engagement and acceptance Barriers are ones you've already heard before. Data is important. Having access to that data is difficult. That includes not just local facilities like refineries or power plants, but also access to the geological data, which is often guarded by commercial interests or national interests. With
Thanks.
that, hand
Yeah,
back to you, David.
well, thank you, and my apologies for the problems with the slide. I had very loud sirens coming by my window here at my office, and I was trying to mute, and that's where somehow I pulled down the slides. My apologies for that.
No.
A third section of our report is on cross-cutting issues. We're just going to talk about a few of those. One of them, very important, is on materials innovation, and Colin McCormick wrote that chapter, and we'll talk about it.
Sure. Thanks, David. Julio mentioned discovering new carbon capture materials. Alp also talked about materials. I want to emphasize that many decarbonized energy technologies rely not on bulk materials used at millions of tons in the economy, but on functional materials. We don't need giant amounts of them, but they need very special properties. They include carbon capture solvents and sorbents that need to have a lot of capacity and fast kinetics, high strength magnets, catalysts, electrodes, etc. Discovering these is tricky. You can do it the Edisonian way and try out thousands of them in your lab. That's really pricey. In the modern era, we've used computing approaches to try to simulate the properties of a material before we ever physically synthesize it. That's also still fairly compute intensive and expensive. AI can speed that up dramatically and help us predict the properties, the bulk properties of functional materials that we've never ever made before to decide whether it's worth making them and testing them in a lab. AI also can do interesting things on the language side. Any functional material you'd like to think about probably already has thousands of research articles published on it, and neither you nor all of your graduate students are going to be able to read those. LLMs increasingly can ingest that literature and synthesize in a sophisticated way everything that's been previously learned about a particular material class. Finally, there have been generative approaches with AI that have proposed entirely new materials classes that no chemist, no material scientist has ever investigated before. And that's an exciting trend. Many barriers here, but they're very similar previously: data availability and trained personnel.
We have a section of the report that looks on data center power demand, which has been one of the hottest, if not the hottest, issues, I think, in energy policy in the United States in the past year. And there's a lot here, but just to offer a few statistics. In 2023, roughly 1.5% of global electricity demand came from data centers globally, about twice that in the US. Interestingly, just by way of comparison, about 4% of global electricity demand comes from aluminum smelters, gets a lot less attention than the demand for electricity from data centers. And there's a reason for that. The reason is that data center demand is growing a lot, growing incredibly fast. One important point we highlight in the chapter is that data center demands coming from a lot of sources, not just AI, 5G network streaming services, social media, online gaming, or other sources of electricity demand for data centers, but AI is the most important factor. We pulled together in this report all of the reports that we could find, and there are about 24 of them that were looking at projections of power demand related to data centers and AI in the years ahead. And we have a chart that gathers all of them. But this is a very dynamic area. It's moving quickly, including in just the past few days, there's been enormous media attention around power demand. And we thought we'd just comment on this. We can talk more about it in the Q&A. This is not from our report from 6 months ago. But as many of you may have read, DeepSeek, a large language model out of China, it's got enormous attention for its tremendous capabilities in the past couple of weeks, and on reports as well that the compute used for DeepSeek was much less than used by comparable models that we're familiar with from the United States. A few observations about DeepSeek. I mean, it does perform at levels comparable to products of OpenAI, reportedly a fraction of the cost, as I just said. This has raised questions in the minds of many about new power supplies for AI and whether they would be needed. Stocks of some major utilities fell dramatically on Monday on expectations that there would not be the massive new need for power that many have thought in recent months. That said, there's a lot of questions about that conclusion because more compute still likely produces better AI, often referred to as scaling laws. Rebound effect, or what's known as Jevons paradox, could be significant here. As things get cheaper, people tend to use more of it. There's important distinctions here between training of models and the use or inference of models. We can get into those in the discussion section. But I think the bottom line is there's huge uncertainty with regards to data center power demand in the years ahead. We've been talking a lot about the opportunities related to AI and the good things that AI can do when it comes to fighting climate change. That said, it is extremely important that we focus on the risks of AI as well, and nothing about our focus on the potential benefits of AI should be interpreted to mean that people should be ignoring the risks or not paying attention to the risks. To the contrary, risks need to be managed, and we examine in our report risks in 3 different categories, as you can see here. One, content risks: bias, invasions of privacy, misinformation, disinformation, and omission of information. AI can create significant problems in all those areas, including related to climate. Safety and security risks are important. Colin and Alp and Julio have already spoken about these in context of specific sectors. And then there's resource risk. AI can cause increased greenhouse gas emissions from power demand, strains on the power grid, and water stress. And we talk about all of those. We have a section on government policy, which I co-wrote along with Mikhail Nachmany, and unfortunately she can't be with us to discuss this today, but we look at government policies generally with respect to AI, and then note that there are very few government policies that are specifically addressed to the use of AI for climate change. And then we explore policies that can promote the use of AI for climate change mitigation and manage any risks, and offer a number of recommendations. One recommendation is that government should prioritize development of climate relevant data, investing in data collection and promoting interoperability standards. A second, that government should use their convening power to facilitate knowledge sharing between experts in climate mitigation and experts in AI. And a third is the government should establish ethical guidelines for developing and deploying AI applications. There's more in the chapter. And on the topic of recommendations, just to close us out, I will turn it over to Julio Friedman to summarize some of our major overarching recommendations in this report.
Excellent. First, pay attention. Every organization working on climate change should consider opportunities for AI to expedite, to accelerate, to improve the quality of their work. Second, governments, business, and philanthropies. Everyone gets to play here. You should all fund fora in which AI experts and climate change experts work together and talk. We have found that climate people talk to climate people and AI people talk to AI people. It'd be good if AI and climate people talk with each other. We think that this is an important recommendation for how to move the ball. Third, government should assist in the developing and sharing of data. This is hugely, hugely important. Often the data involve big privacy concerns. Often these are data that are owned and proprietary. Ultimately, the governments have to assist in the development and sharing of the data so that we can get climate beneficiation from it. And companies that have these data should look at the data and say, well, what can we share publicly with minimal risk to ourselves? Fourth recommendation, developing AI, anybody who is a data center operator, they should disclose their greenhouse gas emissions. That includes a full life cycle basis, so not just the scope 2 emissions from electricity, but also the scope 3 emissions from the embodied manufacturing. It looks like that's a substantial fraction over the lifetime of a data center, as much as 40% perhaps. We need to have better information around that so we can manage it. Fifth, every organization working on climate change mitigation should prioritize AI skill development and capacity building. If not, you are simply leaving a lot of opportunity on the table. It is worth delving into this with substantial interest, earnest commitment of resource and time so that you can use these tools well. Sixth, last but not least, all government agencies with any responsibility for climate change, whether that is an environmental or an energy ministry, should have an AI office or at least an AI officer so that they can scour the landscape, provide advice and input to these decision makers to get better climate outcomes.
Well, thanks, Julio.
David, to you.
Just to wrap it up, just to summarize, this report, the AI for Climate Change Mitigation Roadmap, is available at these URLs. We're going to send around these slides, as I said. It is going to be available in hard copy on Amazon soon. This roadmap is actually part of a series of roadmaps that a number of us have worked on over the years, sponsored by Japan's Ministry of Economy, Trade and Industry and the New Energy and Industrial Technology Development Organization. We thank them for their support. And you can find roadmaps on topics including low carbon ammonia, carbon mineralization, industrial heat decarbonization, and more at their websites. Here are important people saying nice things about our roadmaps. Particularly pleased to just pick out the middle one. Vaclav Smil, the noted energy historian, said the ICEP roadmaps provide essential information on different aspects of our energy systems and how they might change over time. I recommend them for anyone interested in this challenging topic. And just to close out, I want to emphasize that this roadmap is the product not just of the people who have been speaking here today, but of 25 total co-authors and really some extraordinarily talented and knowledgeable people who played a central role in the product here. I want to thank them for their role as well. So with that, I'll pull down the slides, and we are delighted to take your questions. And as we start doing that, maybe I'll just turn to you first, Colin, because there's a chapter in the roadmap that we didn't have a chance to talk about that I think might be of particular interest to some people in the audience, in part because of the horrible, tragic fires in Los Angeles, but for broader reasons as well. And that's a chapter that you did along with Alice Hill at the Council on Foreign Relations on how do you use artificial intelligence to help adapt to climate change. Well, most of our book is on how can it mitigate climate change, but this one, adaptation. You would just say a word about that topic.
Sure. So as you point out, David, this was only a small focus of the overall roadmap, but we did take a look at the use of AI to improve weather forecasting. That's only one component to a much larger adaptation strategy, but it's an important emerging area. What we've seen over the past year to 18 months is a dramatic improvement in the ability of weather forecasting models to quickly and accurately produce forecasts, medium range, sort of week and a half forecasts, using AI, using machine learning. So some examples of this are GraphCast from Google, ForecastNet from NVIDIA. These are models that use machine learning and AI to produce forecasts over that kind of 10-day period, and their accuracy is competitive and in some cases better than the conventional weather forecasting models that are run by national weather services. Those rely on major supercomputers. They are difficult to run without resources. And what's interesting about these emerging AI weather models is that they can be run essentially on a laptop, allowing much, much broader use of accurate weather forecasting across the world. Now, this is a rapidly emerging area. We're watching innovations on this even since we published the roadmap. New AI forecasting models have emerged, so we'll continue to watch that. And I do want to note at the end that the technology itself, of course, does not mean that it will be used or heated or necessarily integrated into a full spectrum effective adaptation system. Many other elements are needed, policy, support, resources. So this is merely one piece of the puzzle, but it's a very important emerging capability that could enable a full spectrum adaptation capacity.
Thanks, Colin. And yeah, we're delighted to answer any follow-up questions on that. And we have some really interesting, good questions in the chat. Let me just start with one on skills and skill topics. And it's from an anonymous attendee who asks, which skills would you say are essential? What are some of the roles that you see evolving? Training models, data engineers, prompting, what else? Anyone want to jump in on that, on what skills we think are needed? Looks like.
I'm happy to start.
Right.
Alp is the deep expert, but I wanted to get this bon mot in first. one of the most important skills that needs to be developed is just familiarity for people who are not users, people who are not coders, people who are not developers. But you need to be able to identify hallucinations. You need to be able to know that hallucinations are a real thing in AI. And so if you're a policymaker or a lawyer or somebody working in regulation, like, you want to have some familiarity with these tools, not only so that you can use them for yourself, but you can find misfires, you can recognize potential risks, and you can mitigate them. This lowest level of skilling is essential and economy-wide, and something I can't recommend strongly enough.
I'll piggyback on that excellent answer and indicate that we are advocating for an increased level of communication between folks who are experts at specific industries, in specific branches or divisions of the economy, and those who have kind of AI expertise. As that communication, increases, we have an opportunity for exactly this to come to play, where domain experts will increasingly be expected to be able to understand what is needed to integrate AI into their own workflows, to solve problems in their own sectors. And that's the only way in which we really can achieve the scale of impact that we are hoping to do here, right? It can't just be that a handful of experts propose solutions and that somehow magically trickles down. If we think about something like agriculture, the applications that we propose in our report are indeed leaning on the fact that we hope that there is a broad adoption of this type of technology across a wide segment of people. So increasing those AI literacy skills in terms of evaluating this technology and being able to integrate it into their own workflows is the first step in that journey.
Colin, did you want to add on that?
No, I think that captured some very key points there. Yeah.
That's great. Well, let me turn to a question from Joanna Smith, who asked a really good and a really big picture question. And Joanna asks, have you weighted the extremely carbon intensive aspect of data centers against the anticipated total carbon savings of your various AI applications in this report? That's a really good question. And to kind of say it another way, kind of, are the benefits from AI going to outweigh the costs from AI in terms of the emissions that are produced from creating AI? And I'll start with an answer, and then let me just see whether any of my colleagues have a different response. My response to that would be, we don't know yet. And the future is ours to write. That is, we know that power for AI is going to cause some greenhouse gas emissions. Building data centers and powering data centers, if you don't use low carbon energy, is absolutely going to cause some emissions. But today, 95% of the electricity for example, in the world is not being used to power data centers. And if we can use AI to advance sustainability with respect to that 95% of electricity, maybe we can get more benefits than the costs. And our report is really focused on trying to help advance that possibility, trying to use AI in a way that is promoting sustainability instead of hurting sustainability. In my view, the future is not yet written on this. In terms of analysis today, kind of, if somebody asked me today, is AI causing more emissions and it's saving emissions? My answer would be the data sets and the research just aren't available to answer that question. We just don't really know. But in the future, there is absolutely tremendous potential for this technology to make a difference, but it could do the opposite. And that's why those of us who are working to help respond to the climate change problem think should be looking at opportunities to use this cross-cutting and powerful technology. Let me turn to any of my colleagues, see whether you'd like to add to that or subtract from that or disagree with that. One of the things we found working on this report is we don't always agree with each other. So please take it away.
I want to add to just a bit of what you said, David. First of all, basically agree we can't be deterministic yet. We don't have enough information. I think there's reason to be alarmed, but there's not reason to be alarmist. As you said, right now, AI uses less than 1% of global energy and probably much less than 1%. It is also true that most of the companies who are doing this have made very strong commitments to using green electricity. Google, noteworthy among them, has said that they are going to do this entirely with zero carbon electricity sources. In contrast to, say, Meta, which has not and is building uncontrolled natural gas combined cycle plants. So the landscape is quite dynamic and wet. I will say that one of the questions we grappled with, and Colin in particular brought this up a lot, is actually we can also use AI to produce more fossil fuels at lower cost. We don't know how much of that's going to happen. We certainly could use AI to create problems for a clean economy as well. So it's not just a question of the energy loads, it's really a question of the use cases as well. This is really choose your own adventure. It's very much up to us. There is no a priori reason why greenhouse emissions should go up with AI use. There isn't. But we may end up causing that because we're not paying attention, or we don't have the right data, or we don't have the right regulations. So it's very much up to us to manage this.
I've heard the metaphor people have said AI is like a hammer. A hammer can be used to build things, but a hammer can also be used to break down walls or even to injure people. So it's a tool, and a tool can be used for good purposes or bad purposes. And AI is, I think it's a reasonable metaphor. AI can be used to do some good things and do some bad things, and we're trying to help promote the likelihood that it'll be used for good things in this particular area.
Right. I would like to say that it could be Thor's hammer or it could be Maxwell's silver hammer, and we don't
know. There's a very important topic raised by Onichia Nwebogu. I hope I didn't butcher your name too much, but you've asked a very important question about the Global South and using AI in the Global South. You asked, do you see any opportunities for how the Global South can utilize AI for leapfrogging in energy? And anyone want to comment on AI in the Global South and the issues around that?
Absolutely. I was just in Kenya last week. This is forward in my mind. Let's start with the fact that we think there's a real issue and risk at the Global South of just data availability and bias. We are really concerned that the Global South may not have tools at their that are accessible to them because people aren't gathering the data and building them into the tools. That bias is something we discussed repeatedly throughout the report. There certainly are many potential applications for using AI in the Global South. Just good example of this is just geothermal exploration. The AI are getting pretty good at that. That's an opportunity for low cost, low carbon, clean electricity in many Global South countries. Kenya, Ethiopia, Indonesia is an excellent case. The tracking and sustainable biomass harvesting is one that's another example of this. Nations like India have a lot of biomass. It's not going well there. Borneo and parts of Indonesia, again, that could be used for good, could be used for ill. So there's real applications for this in terms of tracking deforestation, tracking actual sustainable biomass harvesting, and creating protocols by which that's managed. Like, there's a lot that could be done here. And for economists thinking about how to build out grids in parts of the world where there is simply not enough green electricity at this point, what is the low cost solution to do that? What's the locations for better wind farms, for better solar farms, et cetera? There's many potential applications here. In order for these to manifest well, you have to put focus on that too. These nations should also be thinking about having their own AI experts and their own AI officers. The multinational and regional development banks should be thinking about how to make data available, thinking about how to resource people. This is a missed opportunity for philanthropy. In all of their talk about climate justice, AI is a potentially very powerful tool by which equity can be raised in the Global South. And I don't see a lot of philanthropies necessarily diving in on that topic. So it is a broad, critically important topic, and thank you for raising it. Alp, David, others?
I just like to add that the key word in Onochi's response of leapfrogging, I think, is essential. We have an opportunity for all of the development of AI applications to mitigate climate change that's happening in other nations to serve as an opportunity for indeed this technical leapfrogging, taking the lessons that we learn in terms of data requirements, in terms of adoption of this technology into workflows, daily workflows, and thinking about what deployment requirements, figuring out some of these details from initial explorations, and then taking the more mature solutions and thinking about what needs to be tweaked to be able to successfully deploy it in the unique geographies that we're looking to deploy them, is one way to achieving that leapfrogging from a technical perspective.
Great. I just want to underscore what an important question this is and how much attention the AI in the global south requires broadly. And I think one place that may get attention is in the preparations to COP30 in Brazil, UN COP30 in Brazil, and then at COP30. I think there's a real opportunity to have a conversation about the use of AI for climate change mitigation in the global south around that very important meeting. We have a question on state level issues here, which I thought, Colin, you might like to offer some thoughts on. And I've been thinking some about AI in the States. And Chris Way asks, he says, thank you so much for your presentation today. I want to ask if at the state level, what are some states or state agencies doing on AI or ML for climate resilience? Are they using AI ML for collecting data or using it to make forecasts? Anything you've seen in that area?
Well, multiple answers to that. I think there is a lot of state attention at the legislative level for data centers citing energy demand, et cetera. So we're seeing a lot of legislation introduced right now in multiple states on that topic. In terms of resilience and forecasting, I have seen some of that in terms of understanding potential flood zones, revising flood maps. A lot of that, though, does rely on federal NOAA predictions. So state level capacity to do that themselves is somewhat limited, and certainly there's a lot of reliance on federal capacity. I do think some state agencies are working hard to innovate on that and are partnering with state universities to provide a lot of the intellectual sort of firepower on that and model runs. But I think this point goes to a comment we've made repeatedly, which is the need for trained personnel who can understand how to bring together the AI tools and these use cases. That is, many state energy offices are not resourced to have AI experts on staff who would really be able to pursue these solutions. And that's an area that needs attention. It's not just having an AI office at a national level ministry. It's trying to make sure that capacity goes through to regional, state level government offices as well.
Alp, you have some thoughts on that as well?
I was busy responding to a few comments, so I'm going to, yes, assume Colin did a great job. Maybe hand over to Julio here.
Great. There's some...
David, if I could add something just very briefly,
Please.
it is one of the things that we can't underscore enough is the ability for AI and large language models to help with permitting. This is like a legal and regulatory issue as much as anything else. And right now, in many states, it's just not allowed. Or there isn't a process that is acceptable to many parties. And so trying to figure out how to use that to expedite the permitting of clean energy projects and climate projects, sort of adaptation projects, would be incredibly valuable.
We have a question on materials innovation using AI with the anonymous attendee writes, what is a concrete pun example of previously unthought materials classes that AI is developed? And this is a really important topic, and so I'm glad it's being raised. I'm gonna start with just a comment on materials innovation, its impact on the energy sector, because I remember I had the privilege of serving in the U.S. government starting in 2009. I remember when I served in the U.S. Department of Energy then, and I remember getting a briefing when I arrived there, people telling me that they thought offshore wind would probably never be feasible. And the reason offshore wind would never be feasible was because steel couldn't really handle the corrosive marine environment and was too heavy. And my understanding is that materials innovation has basically made offshore wind possible. We have now non-corrosive products. We have the lighter turbines that can handle the marine environment, and so materials innovation is extremely important when it comes to clean energy technologies. And Colin, just want to elaborate kind of with some more examples and more comments on the role that AI can play with respect to materials innovation.
Yeah, sure. To that particular question, I think I did send type an answer with a link to a research paper that helps illustrate one example of that. It can be hard to really understand the complexities of material science, but that particular example illustrates generative AI discovering, in that case, over 1 million new, previously unknown stable inorganic crystal structures. Translating those into catalysts, magnets, et cetera, is another step. But those are materials that could exist using atoms on the periodic table in a stable form that we had not known about before. And it is hard to really appreciate the combinatorics of this, how many possible types of materials could exist by just combining atoms on the periodic table. It is colossal. So what we've seen mostly so far is this enormous opening of the aperture of the possible materials that we could be looking at. Yeah, we're sort of in very much in a boom on that. And then I want to also highlight, tie a few other things together. Materials innovation here, of course, is not the same as a deployed material manufactured at scale that we can use in a system today. There is a long line there, going through a testing phase, going through understanding how you might scale up manufacturing and integrating it into real products. So this is a foundational research topic that needs to be tied to the whole innovation chain. There have been interesting conversations about how this might impact the global South. In some sense, it's possible to pursue materials that would be particularly helpful for example, leapfrogging, as we talked about. And that can be done largely virtually in the discovery phase. But in order to really test and deploy those, you'll need infrastructure, you'll need scale up, you'll need manufacturing. So as with a lot of what we talked about, the AI piece is only one part of the puzzle. It's not a panacea, and we need to remember that throughout this whole discussion.
That oh, go ahead, Julio.
Yeah, quickly, in the chapter, we talk about a number of applications. There's one sensational example of just newly discovered battery chemistries.
Yeah, that's true.
That are lower cost, earth abundant, these kinds of things. The potential here is that this is the transformational stuff. It's not just incremental. You could have radically new substitutes for steel. You could have radically new catalysts. All of these things are possible in here. And so our recommendation is to make sure that that continues to be fed so that really groundbreaking discoveries can enter the market and go through that scale up Colin described more quickly.
Thanks. And thanks everybody who's throwing in questions. We have lots of questions flooding in. We're not going to be able to get to all of them. I want to say to Julio, Colin, and Alp, if there's any particular topic that you would like to bring in to the dialogue as a matter of priority, let me know. And just jump in with it. But I want to read a great question that we haven't touched on yet from John Flogel, a Columbia student, who asks about modular nuclear reactors and the powering of data centers. And asks, do you see a future for modular nuclear reactors empowering large data centers? Anyone want to talk about that?
Yep, I pointed John towards our chapter. Certainly, I think there is this connects to a few other questions. Maybe let's kind of expand the question. A few other questions around how the rise of AI becoming kind of major drivers of energy growth, whether we expect that energy to come in the form of zero carbon or low carbon energy, or not the case, right? Nuclear falling into that former category. So maybe I'll kick it off and pass it over to both Julio and Colin, who I know you've thought quite a bit about this. But yes, there is an enormous amount of excitement and interest around the rise of nuclear. There are applications of AI to the operations of operating nuclear plants. There are applications of AI to the regulatory environment that surrounds the operations of existing nuclear plants. There are applications of AI to the regulatory process of building new nuclear plants. And of course, small modular reactors are part of that increasingly kind of shifting landscape. Julio, Colin, anything to add to that?
Two key points. The first is indeed nuclear is very interesting. Let's not forget that it requires a fuel cycle, a supply chain of fuel. And so even as we look at whether technology is feasible or not, we need to also be aware of the broader infrastructure and supply chain that would be required to make it operate at scale. The second comment I'll make is that the interest in small modular in particular seems to sort of assume this co-location. I'm going to have my own generation facility at the data center. That appears to implicitly lean away from the idea that you would be grid connected, or you would primarily rely on how we normally do this, put a lot of generators on a shared electric grid that has a lot of reliability because there's so many backup generators. I think people thinking around data center power would do well to look a little bit more carefully at what we've learned through grid reliability and trying to put very high power consuming facilities in standalone mode with their own generator. That's really hard. So I think we need to make sure those two kind of lines of thinking, those two communities thinking about a lot of power for data center, but thinking about grid expansion are really joined at the hip and are thinking along the same lines very carefully.
I would add two very small things. One, the question was asked in the context of data centers using small modular reactors. Remember that it takes ballpark 10 to 12 years to get that up and running. A lot of people are interested in this, including the hyperscalers, including the developers of nuclear power. But in the near term, that is not going to matter. In the near term, people are building uncontrolled gas. And the reason they're building uncontrolled gas is because they can't build more renewables, because they're trying to do that, but combination of supply chains, interconnect queues, permitting, land access, all these other sorts of things. So time doesn't end in 2035. I think nuclear will end up being important and continue to contribute. However, in the near term, it's just not going to be particularly relevant. The second thing I'd say is, keep an eye on the small scale wins associated with this. In the chapter, we talk about things like corrosion improvements, extending the life of existing facilities, increasing the output of existing facilities. There's a lot of stuff that AI can do in the near term that actually would improve the performance, reduce the risks, extend the life, reduce the costs of all of these systems.
Thanks. And just to add that our chapter and the report on this topic was written, the lead author was Matt Wald. I want to thank Matt for his great work on this. And also Rama Ponangi from the Center on Global Energy Policy played an important role in that chapter as well. So if you're interested in more in this topic, please take a look. Let's talk about water use, which is something we haven't talked about yet. We have a question from an anonymous attendee who says the following. There was a story in the Washington Post last fall that focused on the high level of water use needed by data centers for AI-related queries. Approximately a bottle of water to provide a 100-word email generated by AI. Can you speak more about potential water stress due to the use of AI? Do you feel this should be a limiting factor in whether or not people should be experimenting with AI? We have a short section in the report, and this wasn't a major focus, but Julio, you wrote that. You want to offer thoughts on water use in AI?
So sure. So we included the water consumption, not just for the cooling of the systems, but also the manufacturing of the data centers, also the cooling of electricity on the grid. We included all of it, scope 1, 2, and 3 components of the water. So we did a pretty comprehensive analysis. One of the questions asks whether or not we included the cooling associated with that, and we did. If our finding on power is correct, which we think it is, much less than 1%, water is even less than that. People like to use numbers like how many swimming pools does it take. Globally, this is a global average, you use less than 1/10,000th of the daily flow of the Amazon River. It is a tiny, tiny, tiny volume of one tiny fraction of one river. To David's point and to the question, Earth is not homogeneous. These things are not all regionally equal. There are areas where data centers are being built that are water stressed, in Arizona, in Nevada, in parts of even Virginia. The demand is getting to the point where there is some water stress. I would encourage people to think about this the same way that we encourage people to think about this for electricity. We don't have the data we need yet to say much. We think the risks are small, but the growing demand could create additional problems, and you want to track that. Most importantly, even including manufacturing of steel and cement and the cooling of the electricity, which is a very large fraction of that, the total numbers here are very, very small. And so we would encourage people to sort of take a breath, think carefully about what they're looking at.
Let me just pause and ask Julio, Colin, and Alp if there are any questions that you've answered or are looking at that you particularly want to bring to the conversation that we haven't touched on already. There's so much to choose from here. One broad topic, a number of people have asked about generally the use of AI in the power grid. Somebody asked, what are the most important uses of AI in the power grid? We have a chapter on this, and the list is long, and and we spoke about this some in the main presentation, but let me just highlight some of the important uses of AI in the power grid. Certainly AI is helpful for it in the generation side, for example, locating generation assets or figuring out the optimal location. It's helpful for renewable power, and today already we're seeing 10 to 15, 20% improvements in output from solar and wind farms from the use of weather data and machine learning tools. It's very useful in transmission with dynamic line rating. Colin spoke about this, and electricity is dangerous in large quantities. You need to manage it very carefully with dynamic line rating, which is sensors on transmission lines. Using machine learning tools, you can put more clean electrons through transmission lines. There's great opportunities in terms of improving the interconnection queue that Colin referred to, and using machine learning and large language models in particular. And then I think materials innovation has potential to improve electricity generation a number of ways, and there's more. So there's just an enormous amount of opportunities for AI to help with reducing emissions from the power grid. And as Colin highlighted, that's extremely important, because today power grid is 28% of global greenhouse gas emissions, but it's going to be more as we decarbonize. We need to both grow the grid and decarbonize the grid at the same time. So we need tools like AI.
Great. David, I do want to address another question that came in.
Right.
It's a question about whether AI can be used for emissions monitoring. And we did write a whole chapter on this. It's worth maybe giving a couple of highlights on that to sort of refresh our memory. The answer is absolutely yes. And this is a tremendously important area. We talked about two broad types of that. The first is around better understanding methane leaks. In particular, we increasingly understand that methane, a potent greenhouse gas, is emitted from oil and gas infrastructure, from combined agricultural feeding operations, and a number of other sources. We do see the use of a combination of remote sensing and AI being increasingly able to pinpoint those methane emissions that may have previously gone unreported. And in some cases, that has led then to mitigating them, to eliminating leaks, fixing flares that went out, trying to patch things. It doesn't always do that. As we've talked about several times, that's only a piece of the solution, but that's a tremendously powerful capability we've seen come online very recently. The second piece was around CO2 emissions, particularly around power heavy industry. Increasingly, there's data sets and approaches like Climate Trace that can similarly leverage larger remote sensing, but also a range of machine learning techniques that can identify CO2 emission sources at very high spatial and temporal resolution, really understand quantitatively on an equal footing across the globe where these emissions are located and how big they are. So yes, it's an absolutely key area and an exciting one to watch.
As a quick sort of soundbite on that exact point, Environmental Defense Fund, EDF, has a space program now. And the only reason they have a space program is because of AI. AI powers all of their analysis that lets them do the things that they do to monitor methane emissions. I wanted to speak to another question that came in around the lack of focus on weather prediction and adaptation and these other sorts of things. Um, I think David said this in passing, but it bears repetition. This is a labor of love for the 25 authors who were involved in this. Many of us are international class experts with a whole lot of demand. We made a decision early on that we just could not take adaptation on as a topic. It was so large, it was so broad, it touched so many different aspects of the world, whether it was agriculture or urban planning or civil safety or migrations or all of these other sorts of things. We just couldn't do it justice in the time that we had. It's not that it's not important, and it's also not that AI can't help. AI certainly can help in all of these things. And in fact, it is unfortunate that this topic has not received more attention. We felt it was critical to focus on the mitigation and energy aspects first, uh, kind of like the IPCC does, but we recognize the point and hope that others will take up that gambit and focus on that important topic.
Yeah, amen to that. We're down to the last few minutes here. We have one somewhat technical question, but I think it might be worth bringing out about computer-aided engineering and simulations. And Colin, see if you have any thoughts on that. The question asked us to elaborate on the point of AI supporting faster simulations and iteration times. How exactly does AI expedite this process? Any?
Sure, I have a brief answer to that, but a good example is in computational fluid dynamics. If you want to understand how air or water would flow through any sort of system, like a boat hull or like an airplane wing, typically we run complicated, intensive calculations to compute that for every single design iteration. And that's slow. You can't innovate very rapidly. Machine learning algorithms can take previous CFD runs and learn the patterns of the answers, similar to how Alp described learning patterns from previous training data. Then those emulator algorithms can say, if you ran a full computational fluid dynamics calculation over a long period of time, here's what you probably would get as an answer. In many cases, great, thanks so much. You just saved me a ton of time. I got an accurate enough answer to know this was a bad design. Forget it. I'll try something else. Or, seems like this design is starting to look pretty good. It might be worth doing the full calculation after all. So that's one more concrete example of how engineering design cycles can be accelerated.
Well, let's close with the breaking news of the week and talk about DeepSeek and issues there. And Siri Hedron, a reporter with S&P Global, asked us, should utilities or utility regulators be revisiting their electricity demand forecasts in light of DeepSeek? Alp, you want to get us going on that and then see whether other people have related thoughts?
Yeah, I also shot a short answer back to Siri there, and I think certainly, but it's important to drill down on what the DeepSeek technological advance really means. So what this proves is that through engineering developments, in this case, cheaper hardware and clever mathematics and algorithms, that what we thought was only achievable in one way is achievable in maybe more than one way. So for the purposes of training these types of large language models, we now have evidence that that could take indeed much less energy and much less money. However, this does not give a commensurate reduction in energy requirements during the usage of such models. So it's important to make sure that we disassociate the enormous energy requirements that go into training these models and the costs, but also the usage of these models, which would be through a much more kind of scalable, consumer-driven fashion. So I think that this means that we should be thinking very carefully about what our forecasts mean, but that there's still an enormous amount of uncertainty as we look forward in terms of what direction this is going to take, whether this is going to lead to much higher consumption of this type of technology, or a stable level of consumption, but just reduce costs to train these models. Lots of potential outcomes. So I'll start there and curious to see what my colleagues think.
You want to jump in? Or
Colin, you first.
Well, no, I mean, I think I'll captured key points there. Utilities are, of course, also engaged in understanding load growth in many other sectors. So let us not think that it's dominated purely by this, and that we can sort of answer that purely on the basis of this possible new advance from DeepSeek. And Alp is right to sound a note of caution about what we really know and really don't know. It remains opaque. But I'll leave it there.
Yeah, so I think a couple of things. First of all, this underscores how dynamic this landscape is, how fast things are changing, that people's predictions on all kinds, on all fronts, can be quite wrong. And there's a lot of things we don't know. It's actually why it's so essential to just gather data and learn about these things. As Colin and Alp sort of indicated, right now the growth in electricity demand in the United States, maybe a quarter of that is AI. Two-thirds, the other three-quarters are not. It's onshoring manufacturing, it's electrification of vehicles, it's all kinds of things. So should we revisit those assumptions as well? Maybe, but it's not the only basis of this rapid load growth. NVIDIA got $500 billion in stocks over 4 months. It was erased in 1 day, and then it's back up 10%, right? Because in fact, as we're learning more about DeepSeek, people were like, oh, maybe they were using NVIDIA chips to do it, and they didn't report that because it's China. Maybe the actual energy usage was not as low. As Alp said, maybe the use case looks different than the training case. As that stuff is starting to shake out, we are in real time reassessing the energy implications, the manufacturing implications, the use implications for these tools. And so part of what I've taken away from working on this project is a sense of humility. There's only so much that we can really know here, and there's only so much we can really state with confidence. The one thing we can say is AI is not getting smaller and it's not going away. The demands will grow, the use cases will grow in medicine, in military applications, in conventional energy, and all kinds of things. We think it's important that it's focused on trying to resolve issues of climate as well.
Julio, those are great notes to close on, and we are at the time for closing. I just want to end by thanking a number of people. First, by thanking the great team at the Center on Global Energy Policy that organizes our events and organizes this webinar. You do great work, and we're really grateful to you. I want to thank all the co-authors of this report. As I've said a few times, only a few people on screen here, but this was an enormous team effort with great contributions by everybody. I want to thank our colleague, Mikhail Nachmany, who couldn't be on the call today. I want to thank Julio, Alp, and Colin, and then I want to thank all of you who took the time to engage with us. We're sorry we weren't able to get to all of your questions, but we are going to send around a copy of our PowerPoint deck, and please write us. We look forward to engaging with all of you on this important topic. Thanks, everybody, and have a great day.